Okay. Are we ready?
Yes.
Good. Okay. Good afternoon. Welcome everybody to our character varieties and heat bundle session within the framework of IMAC. Our first speaker is Alfonso Zamora from Universidad Politécnica de Madrid, and he will talk about the invariant for principal bonding. Happy to have
Okay, so thank you all for being here. Thank you, Ronald, for the invitation and all the organizers for bringing us in hybrid mode online this time to Costa Rica, but still somehow in Costa Rica. So thank you. So the story I will tell you today is a joint work very much in progress with George Hitching, where we are trying to explore the idea of the Segre invariant and the Segre stratification for principal G bundles, a notion which is already quite known for a long time for vector bundles. So let me first recall the idea of the Segre function or Segre invariant for vector bundles, and then I will tell you what are the first results we are getting in the principal bundle setting. So this story goes back quite old in time. And the setting is the following. So X will be a complex algebraic curve of genus G during my talk. Then there is this kind of seminal paper by Lange and Narasimhan in 1983 for rank 2 vector bundles. And they define this Segre function, this number, which is the degree of the rank 2 vector bundles minus 2 times the maximal degree of any possible line subbundle. Then we observe that the stability is related to the positivity of this function, because if the Segre invariant is positive, then this is equivalent to the function being positive. Then this is equivalent to the slope of the rank 2 vector bundle being greater than the maximal possible slope of a line subbundle. Since the only possibility for a rank 2 vector bundle to be destabilized is by rank 1 subbundles, by line subbundles, then this is equivalent to E, the vector bundle from the very beginning being stable. Then this Segre function, this number measures the degree of stability of the vector bundle. Then Lange and Narasimhan studied this because they wanted to translate to the moduli space of rank 2 vector bundles a former idea going back to Segre's result in 1889, where he studies the intersection theory of rule surfaces. We know that a rank 2 vector bundle, the projectivization of a rank 2 vector bundle is a rule surface, and then lines and bundles correspond to sections of this rule surface. Then he studied the self-intersection and the numbers occurring as self-intersections of sections in the rule surface. He understands these numbers and the geometry of this number through second varieties. And then, time after this, there is these two results by Nagata and Maruyama. Nagata proving that this Segre, this number, which by that time is kind of known as the Segre number or the Segre invariant, for a rank 2 vector bundle is less or equal than the genus. And then Maruyama studies what happens in particular. So what are the number of possible stabilizers for each value of this Segre invariant? When the Segre function achieves the value of G, the genus of the curve, then we find a one-dimensional family of possible of maximal line subbundles achieving this maximality condition of the degree. And when the Segre invariant is less or equal than G minus 1, then there is a finite number of maximal line subbundles, and that count is computed. So there's 2 to G maximal line subbundles when E is general. So there are particular cases in the modular space where this does not happen, but in general, for general E, we have this count. Then the following step in the process is the paper study of Letizia Brambilla and Herbert Lange in 1997, when they generalized these to higher rank vector bundles. And then for a general rank vector bundle of rank R, we find that a vector bundle can be stable or unstable if it is destabilized by subbundles, but then the subbundles can have different ranks. So the possibility of being destabilized by subbundles of different ranks means that in the sense of defining a general Segre function for general rank vector bundles, we need to fix the rank of the subbundle we are checking as a candidate for stability, as a candidate to destabilize the vector bundle. Then the generalization is the following. Fixing K, we have different invariants. So Sk of the vector bundle E is K times the degree of the vector bundles minus R, the rank of the vector bundle E, times the maximal degree of those subbundles of the prescribed rank K. Then if this function is positive, that means that the vector bundle E cannot be destabilized by subbundles of that rank. And if all the functions for all different Ks are positive, that is equivalent to stability. So for a vector bundle to be stable, we need all these functions for the different Ks to be positive. Moreover, they prove a series of results. They show that for each of these ranks, the function Sk is semi-continuous. So when we have a family of vector bundles varying over a base, that function is semi-continuous, which allows to stratify the modular space into different strata labeled by the different values this invariant is achieving. So we fix K, and then for the different numbers S, where this K invariant, this K Segre invariant is achieving the value S, we get a stratification into locally closed subschemes of the modular space. And they also compute different features of the geometry of this stratification. They compute the dimensions, the irreducibility of the strata in this situation. Then all other results related to this story are the results by Russo and Monserrate-Fido in 1999. They show that generic stable bundles in this stratification can be written as extension of stable bundles. So this means that for generic members of the stratification in the different strata, we are able to produce extensions which are measuring how many sections these vector bundles have. Then this relates to Brill-Nettel theory and the stratifications coming from the number of global sections that a vector bundle has. And another item is the bounds of these Segre invariants. The first bound comes from the former paper by Nagata, and then Mukai Sakai in 1985, and then Hirschowitz in 1986, which proves the sharpness of this bound. They show that this Segre invariant is bounded by this quantity, which depends on the invariance of the problem and depends on this mod R number. So there are different bounds depending on the arithmetics of the invariance involved in the process. So this is more or less the story for vector bundles. And then Song Cho and George Hitching in a series of papers 2012, 14, and 15, they translate this story to the symplectic and the orthogonal case, which are the first cases of, or the easiest cases of principal bundles, which are the objects of our current study. So a symplectic or a orthogonal bundle can be described both at the same time. Is a pair consisting of a vector bundle and a morphism of the tensor power of the vector bundle, which itself to the structure sheaf of the curve. The vector bundle appearing here is a rank to n in the symplectic case, or it could be both even or odd rank in the orthogonal case. And then the morphism phi is skew symmetric or symmetric, depending on the symplectic or the orthogonal case we are considering. I recall that we call a subbundle to be isotropic under these circumstances if the restriction to the subbundle of the morphism is 0. And we call a subbundle Lagrangian, or in the orthogonal case, maximal isotropic if furthermore the rank is maximal. So the rank of the subbundle is half the dimension in the symplectic case, or the floor of half the dimension in the orthogonal case. Then they define a Segre type invariant, which is this T, which is the negative of 2 times the maximal degree of a maximal isotropic subbundle. I also recall that the definition of symplectic and orthogonal stable bundles coming from theory of Ramanathan, and there are many studies of these kind of bundles. We say that a bundle is stable if for every isotropic subbundle, but not necessarily maximal, then the slope of the isotropic subbundle is less than the slope of E. By construction, the degree of these bundles is 0, then this is equivalent to the degree being negative or minus the degree of the isotropic subbundle being positive. Then E is stable. Then if the orthogonal or the symplectic bundle is stable, this Segre type invariant is positive, but not the other way around. Why? Because it could happen that a symplectic or a orthogonal bundle, it is unstable, it is not stable, because it is destabilized by a not maximal rank subbundle. It could be destabilized by a lower rank subbundle, which is not measured by this maximal isotropy condition. So for this particular Segre invariant, so for this particular invariant measuring whether a orthogonal or symplectic bundle is destabilized or can be destabilized by a maximal isotropic subbundle, they produce the same kind of results. They produce the semi-continuity of the invariant, hence a stratification of the modular space into the different values of this Segre invariant, and they study the reducibility dimensions of strata. In another 2 pieces of work with Cheong, they count and they interpret the number of Lagrangian subbundles of maximum degree. So they have a generalization of this result by Nagata and Maruyama. And there are also some results for orthogonal bundles of lower rank, of rank less or equal than 6, regarding what happens with isotropic subbundles of not maximal rank. So, for example, if the rank of E is 6, then a maximal isotropic subbundle has rank 3. But what happens if the stability condition is broken at rank 1 or at rank 2 moments? Then we find these other Segre type invariants. We can call them S1 or S2. So this is more or less the story so far. So let me define what we are considering in the work in progress we are carrying. So let G be a connected complex reductive linear algebraic group, and let E be a principal G bundle over a curve X of genus G. Then I recall the notion of stability by Ramanathan. E semi-stable is for every maximal parabolic Q and a reduction of the structure group to this parabolic. Then the degree of the normal bundle of this reduction is positive in the strictly stable case, or greater or equal than 0 in the semi-stable case. This n sigma is the normal bundle on the image of by this section sigma. Then, for those not familiar with this notion, let me recall this easy example. So, if G is GLR, then we know that principal GLR bundles are the same, are equivalent to rank R vector bundles. Then what is a maximal parabolic? So a maximal parabolic is under a choice of Borel or a basis. Our matrices are block triangular matrices of this shape. So A, C, and B, and the lower left block is 0. Then Q can also be seen as the stabilizer of subspace of the R-dimensional total space, which is the fiber of the vector bundle. Then a section, what yields is a vector subbundle. So having a section of this maximal parabolic is the same as having a vector subbundle in the classical vector bundle notion of stability. And the normal bundle is the bundle of homomorphisms from F to E over F. And then the degree of this normal bundle is just a classical computation of what is the degree of this homomorphism bundle. So playing with the degrees and the ranks of the pieces involved here, we arrived that the degree of this normal bundle is exactly up to multiplications by the ranks. It is the difference of the slopes of the vector bundle and the candidate to be a destabilizer. So the minimum degree of a normal bundle exactly coincides with the same value of the Segre function we defined for vector bundles. So this, in this case, is why we call this a generalization to the principal bundles setting. Then the definition of the Segre invariant is the following. So given P, a parabolic subgroup, this parabolic subgroup now is a general parabolic, so not necessarily a maximal parabolic. The Segre invariant of a principal G bundle E is the minimum of over all the possible degrees of reductions to this parabolic. So this is the number we are studying. So let me just quickly give you an overview of the results we have so far. So first, we are able to produce a stratification or a similar kind of stratification as people had for vector bundles. So the result is if we have a family of principal G bundles varying over a base B, then EB is the restriction to the slice to the restriction to a point in the base B. We fix a parabolic P, then for every integer S, these sets, so the points in the base B for which the Segre function is less or equal than S, this is closed, and the function over the base B is semi-continuous. This allows to produce a stratification of the moduli space of G bundles. So if Mx G delta is the moduli space of principal G bundles, fixing the topological type delta, we fix a parabolic P, and then we have this joint union of the moduli space into these pieces, where each piece is a locally closed subscheme where the Segre function for the parabolic P achieves the number S. I have been called this Segre number or Segre function a Segre invariant for a while now. So let me say something about why this is an invariant. So what are the invariance properties of this function? In the vector bundle story, if we have a rank R vector bundle and we have a line subbundle, then it happens that the Segre function is invariant by tensoring the vector bundle by a line bundle. In fact, this can be understood in a more general sense because this Segre function is determined by the associated adjoint bundle via the surjective homomorphism from GLN to its adjoint bundle, which is PGLN. So this is more or less the situation we encounter in the general G situation. And then we have this bunch of results exploring that situation. So if we have phi, which is a surjective homomorphism of groups, and we have a parabolic which contains the connected component of the kernel of this homomorphism, we have a principal G bundle and the associated H bundle via this homomorphism, and we have a family of principal G bundles. Then there are several invariance properties. So the Segre function for E's, for the G bundles, coincides with the Segre function for the H bundles with the parabolic, which is the image of the parabolic of G. Then the sets of points in the family, so the sets of the fibers where the Segre function takes a particular value, coincides with the set of points where the associated bundles take the same Segre function for every value of the Segre function. Then this also produces, so the map between G and H produces a map of between the moduli spaces, between the G bundles, the moduli space of G bundles and the moduli space of H bundles with the corresponding topological type. Then we have that the stratification has a correspondence by the preimages of this map as this. So these are the strata on the H side, and these are the strata on the G side. Furthermore, this is in general not surjective, but if moreover this is surjective, then we have something more. We have that the number of S appearing in the stratification of the moduli space, so the number of values of the Segre function for which there exists a stable bundle in the moduli space achieving that value of the Segre function coincides with the values occurring similarly in the H picture. This, for example, applies certain examples we are exploring. This applies, for example, to the surjective homomorphism from spin R to SOR. This has kernel C2, which is contained in the center of the spin. We know that the center of a spin has three possibilities depending on the arithmetics of the order of the spin. And then for the trivial topological type vector bundles, we have this surjective homomorphism, where we should be able to relate particular features of the geometry in both moduli spaces of the stratification. Finally, the Segre invariant is an invariant of the conjugacy class of the parabolic. So if we conjugate the parabolic subgroup, then we find an invariant which takes exactly the same value. And let me just finish by saying that, well, essentially all the things which are known before as particular examples are of maximal parabolics. So are for maximal isotropic subbundles in the symplectic case or in the orthogonal case, or maybe not maximal isotropic, but subbundles, which corresponds in the language of parabolics to maximal parabolics. So we are trying to produce examples of parabolics which are not maximal. So for example, even for vector bundles, so for GL3 rank 3 vector bundles, if we consider as a parabolic the Borel, then reductions of E to the Borel are flags of a line subbundle or rank 2 subbundle indexed by a tuple of degrees. Then we are trying to understand what can be said about the geometry of this stratification, and well, we conjecture we are making progresses on this particular values of the conjecture. So for particular values of the invariance involved in these reductions, we conjecture that there exists an irreducible component for each tuple of degrees in the flag, whose generic element is stable. So generically, they appear in the modular space of vector bundles with the prescribed value of the Segre invariant. And using a careful search with the geometry on the exact sequence and the diagrams of the vector bundles to compute the dimension of these generic irreducible components, and being able to show that these components are not that strange, are equidimensional. So even though they can have several components, all of them are of the same dimension. So I think it's time. So I'll stop here and thank you for your attention.
Thank you, Alfonso. Maybe it's a good idea. Sorry, there is some echo. Thank you, Danny. Maybe it's a good idea to start with questions and observations from the online participants. Are there questions or comments? they're online. So I don't know if here in the audience are there questions or comments for Alfonso? No. So let's thank Alfonso again.
Thank you.
Okay, our second speaker is Edgar Castañeda from Universidade Zacatecas, and he will talk about modular spaces of Higgs coherent systems in the stable case of record. Edgar, can you hear me?
Yeah, I can hear you. Can you hear me well?
Yeah, a bit. Can you? Does everybody hear Edgar?
Can you hear me now?
We can hardly hear you.
Can you see the slides?
It's better now. No, we cannot.
Not really. I just see a black screen in your cursor. Share again. What about now?
We still cannot see it.
Only a black screen still. Sorry. Strange. Sharing the screen.
Maybe someone else can share the slides if.
It's a good idea. Edgar, maybe you can send me the slides and maybe we can.
Yeah.
Or put them on the chat.
Yeah, that's a good idea.
Recording in progress.
Okay, good. There they are, Edgar. Thank you. So, as I've already said, our second speaker is Edgar Castañeda from Universidad Zacatecas, Mexico, and he will talk about moduli spaces of Higgs coherent systems. Sorry, in the stable case over a curve. Thank you very much for being here, Edgar.
You are muted, Edgar.
Now you can hear me?
Yes.
We can hear you.
Sorry for this. Well, thank you all for being here. I would like to thank Professor Ronald for the opportunity to be part of this event. The talk consists of two parts. In the first section, I will describe the moduli problem of Higgs coherent systems over a curve. Its objects are unaugmented bundles related to Higgs bundles. Then I will discuss the construction of the moduli space for these objects when we assume some stability on the underlying vector bundles. So let me start with the moduli problem. I will follow the approach of Professor Newsted's book by introducing the main objects that characterize a moduli problem, which are the elements, the equivalent relation, and the notion of families. Through all the talk, X denotes a smooth projective curve of genus at least 2 over the complex numbers. Omega sub X denotes its canonical line bundle. And I also fixed 3 integers, n, d, and k, where n and k are at least 1. A Higgs coherent system of type ND is a pair consistent of a holomorphic vector bundle E together with a k-dimensional subspace B of the space of Higgs fields. We denote by H and K the set of all Higgs coherent systems of fixed type. Let me make some quick remarks about this set. In the line bundle case, the study of this object reduced to the study of line bundles together with holomorphic conforms over the curve. And for higher rank, this set is not empty, since we can construct decomposable vector bundles with many Higgs fields. And by Serre's duality and Riemann-Roch theorem, we can see that the values of K implies conditions on the vector bundle, as we can see in these two cases. For example, if the vector bundle is simple, we know that K has to be less or equal to this number. And well, now we define the equivalent relation in this set. For this, we consider isomorphism alpha between E and E prime. This map induces morphism between the corresponding Higgs fields that I denote that hat alpha, and is defined as this conjugation And we say that two Higgs coherent systems, E, B and E prime, B prime, are isomorphic if the underlying vector bundles are isomorphic and the induced map preserves the vector space structure of B in the sense that it maps B to B prime. Note that this definition is an extension of the usual notion of equivalent relation for Higgs bundles. The next ingredient in the moduli problem is the notion of family. In this case, a family consists of a family of vector bundles E together with a subsheaf or rank K of this associated sheaf that I call R1 sub E dual. This sheaf is constructed using the family of vector bundles and the first direct image with respect to the projection to the second factor. And we consider this sheaf because its fibers are exactly the space of Higgs fields. So a family is defined as a pair E, B, where E is a family of vector bundles of fixed type, and B is a subbundle or rank K of this associated sheaf. Equivalence between families is defined as in the case of Higgs bundles. That is, two families are equivalent if the Higgs coherent systems are isomorphic at each point. Summing up, the moduli problem for Higgs coherent systems over a curve is defined in this way. For the notion of induced family along a morphism, we take the pullback in each entry. And our goal is to determine whether the space of isomorphic classes admit an algebraic structure that reflects how these augmented bundles deform. But before moving on, are there any questions at this point? If not, let me continue. As you may expect, the presence of automorphism of these objects prevents the existence of a fine moduli space for all Higgs coherent systems. For this reason, and following standard approaches in the study of augmented bundles, we consider Higgs coherent systems where the underlying vector bundles are stable. For the construction of this moduli, I use some known results about the moduli space of vector bundles, such as the fact that this moduli is smooth. In the coprime case, there exists a universal family parameterized by this moduli, and the tangent bundle of this moduli has fiber that can be identified with the dual of the Higgs fields. Moreover, in this case, when the underlying vector bundle is stable, we can describe the equivalent class of this kind of Higgs coherent systems. To do this, we study that object that provides a way to measure how many subspaces of the Higgs fields correspond to non-isomorphic Higgs coherent systems. And in the case where the vector bundle is stable, the following proposition tells us that each element in the Grassmannian determines a different isomorphic classes. The results follow from the fact that isomorphism between stable bundles are multiplication by a non-zero scalar, so the induced morphism in the Higgs coherent, in the Higgs fields does not change the vector space structure. From this proposition and the properties of the model space of stable bundles, we obtain the following result. The relative Grassmannian of the tangent bundle to the model space of stable vector bundles is in one-to-one correspondence with the space of isomorphism classes of this kind of Higgs coherent systems where the underlying vector bundle is stable. This shows that this space of classes admits an algebraic structure and partially resolves the moduli problem. The next question is if there exists a family with universal properties. To answer this question, we consider the following pair. By the coprime condition, there exists a universal bundle over the moduli space. Pulling back along this morphism, we obtain a family of stable vector bundles parameterized by this Grassmannian bundle. And over this Grassmannian, we also have this universal exact sequence. And in particular, the tautological bundle has rank K. So we have a family of stable bundles and a family of k-dimensional subspaces. But is this pair actually a family of Higgs coherent systems? The next result shows that it is. As we can see, we only need to check that the tautological subbundle lies in the correct direct image. But this follows from base change. We obtain that equalities that relate the first direct image and the pullback. And by the properties of dual and pullback, we obtain that the direct image that we need to check is isomorphic to the pullback of that one. And by the universal property of this bundle, we have that direct image is precisely the cotangent bundle to the moduli. This geometrical interpretation is the reason why we consider first direct image in the notion of families. Using this family, we can prove the existence of the moduli space for Higgs coherent systems where the underlying vector bundle is stable. We only need to check that this family satisfies the universal property. So if we take another family, E prime, B prime, by the universal properties of the bundle E and the tautological subbundle, we can prove that the Higgs coherent systems at each point are isomorphic. Then this Grassmannian, together with this universal family, gives a presentation in the category of smooth irreducible projective schemes for the moduli problem of Higgs coherent system in the stable case. As a side remark, working in the tal topology, we can drop the coprime condition and prove a local version of this statement thanks to the local existence of that universal family over the moduli space of stable vector bundles. For the general case, the existence of the moduli space of Higgs coherent systems without assuming stability on the underlying vector bundles, we can use geometric invariant theory. There exists a parameter scheme together with a linearizable action of a reductive group. This action gives a one-to-one correspondence between the isomorphic classes of Higgs coherent systems and the orbits of this action. Hence, the moduli space of Higgs coherent systems is constructed as a Yeti quotient. In particular, This module space is the quotient of a subscheme of this Grassmannian bundle of that tangent of that cotangent bundle, where R denotes a subscheme of this Grothendieck scheme and is quotient by the action of that special linear group. We also can prove that in the stable case, there exists a linearization such that the JT quotient corresponds to the Grassmannian bundle we construct previously. It is important to mention that the ideas used in the stable case are exactly thus behind the JT construction, which highlights why study this case first is particularly relevant. Well, that's what I want to talk today. Thank you for your attention.
Thank you, Edgar. Are there comments for Edgar?
I have a question.
Sure.
Edgar, do you use some stability function as like the stability function for coherent systems?
The JT stability is a work in progress, but I think I have something to say in the slides. For the stability function, we are working with these cohomology spaces that geometrically have some meaning. For example, the first one measure the Higgs fields that are nilpotent. And in rank 2, we have this function, but off the record is just a guessing at this moment. And the function depends on the slopes of the vector bundles and these quantities that appear in blue and green that is related with the invariant subbundles under some subspaces.
I see, thank you.
Thank you.
So what you compute here in the bottom is like the Hilbert-Mumford criteria.
Yeah,
that will hold
exactly.
these invariants, this inv and nil.
Yeah, exactly. And in rank 2, we have that formula because we know all the nilpotent Higgs fields in this case, and all the nilpotent Higgs are precisely that cohomology group. In higher rank, I'm not sure about. But yeah, we try to compute the Hilbert-Mumford criteria.
Great, thank you very much.
Are there more questions or comments for Edgar? If there are not, then thanks Edgar again.
Sorry, Ronald, if you're saying something on the microphone, we cannot hear you.
You cannot hear me? It seems you cannot.
Very low.
Sir, can you hear me?
We hear you, but very low.
Do you hear me now?
A little bit better.
I will try the other microphone. Do you hear me?
Yes, just about. It's very weak, but we hear you.
Do you hear me now?
Yeah.
No?
Yes, you can hear. It's not very loud, but you can hear.
One, two, three. Do you hear me? Do you hear me, Peter?
Yes, 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 I hear you now, yes.
Good. Okay. So do you hear me clear? Peter?
Yes, yes,
Yep. Is all right?
yes.
We have kind of a delay with the signal probably, but even so. Okay. So our third speaker is Peter Gothen from Universidade de Porto, and he will talk about the conformal limit and projective structures. We are glad.
Oh, just. Okay, so thank you very much, Ronald, for the introduction and for the opportunity to speak here. So, can you see my screen? Yes. Okay,
Yes.
great. Let's see. I think it looks as if it's a bit too big. Maybe this is better. Okay, so yeah, it's a pleasure to be here, even if it's only virtually. It would be nicer if to be there in person, but but anyway, so let me get started. So I'm going to talk about the conformal limit and projective structures, but it's really also mainly about Higgs bundles. And this, I should say, is joint work with my former student, Pedro Miguel Silva. All of what I'm going to talk about. Okay, so what I'm going to talk about is well, yes, I said it was about Higgs bundles and this conformal limit construction or idea of Gayotto, which in some sense is related to the C-star action on the moduli space of Higgs bundles, and the conformal limit itself. Well, its definition and its existence is known, but I'll start by reviewing that part of the story because it's a very beautiful story, and then I'll talk a little bit about at the end our contribution, where what we do is we interpret this conformal limit in a geometric way as a deformation of CP1 structures on the underlying Riemann surface. Okay, so let me just start with reminding you about the Higgs bundles, what's the Higgs bundle, and the non-abelian Hotz theorem. So I'm going to start with a closed Riemann surface of genus greater than or equal to 2, just so that we do have some stable Higgs bundles on it. And we already saw in Edgar's talk essentially what is a Higgs bundle. So it's a pair which consists of two things, a holomorphic bundle E on our Riemann surface. So since I'm concerned with just SL and C Higgs bundles, actually the underlying C infinity bundle can be taken to be the trivial bundle. And the data that defines a holomorphic bundle is, I'll take it to be this d-bar operator, which tells me when there's a smooth section of E, when is it holomorphic. So that's exactly when it's killed by this d-bar operator. And then we need a holomorphic Higgs field. So I want it to be holomorphic, and the Higgs field. So here I'm writing it as a 1-0 form with values in the traceless endomorphism. So since it's holomorphic, it's exactly a section of the endomorphism bundle. It's a holomorphic one form with values in the endomorphism bundle. And because I'm fixing the determinant, we should look at traceless endomorphism, which is this 0, and yeah, so we should take the trivial determinant bundle. Okay, and the non-abelian Hotz theorem tells us that if we have a polystable Higgs bundle, then we can find this harmonic metric on it. And what is a harmonic metric? Well, it's one which allows us out of the Higgs bundle data to build something more. So we can take the Chern connection given by the harmonic the metric here and the d-bar operator. We can take the adjoint of the Higgs field with respect to the metric. So this is a metric on the bundle E, and then the condition that this metric be harmonic is exactly that we have get a solution to this famous Hitchin equation. We still have the holomorphic condition and this auxiliary condition. Okay, so that's like half the non-abelian Hotz theorem. The other half is that if we now take our harmonic bundle and write down this operator, dB, which we can concoct out of our data. So we have the d bar e and the phi here, and then we take the other bit that came from the churn connection and the adjoint of the Higgs field, write all down these operators, and the point is we get a flat connection. So this Hitchin equation basically tells us that this connection is flat. Okay, and the other half of the theorem is then that this construction can be inverted. So this connection, if you have a flat connection, which must be reductive, you can also find a harmonic metric, and then you can get back a polystable Higgs bundle. Okay, so that's the non-abelian Hodge theorem. So because of that, you have this famous hyperkähler structure on the moduli space of Higgs bundles, which was indeed one of the motivations why Hitchin came up with it in the first place. He wanted some examples of hyperkähler manifolds, and here's how we might understand that. So if we think on the one side, on the moduli space of Higgs bundles, which I write here as M Dolbeau, this is Simpson's terminology, then at that side we have our Higgs bundles, and at the other side, using the non-abelian Hodge theorem, we get this flat connection, which I wrote here as nabla B. And well, let me put it like this. So you have a flat connection, but you can split it in two parts. Let me just go back here. So if you take your flat connection and take the 0,1 part of it, then you get a d-bar operator, which defines a holomorphic structure on your C-infinity vector bundle, which is different from the one you had before. And then you get this with this part, which is then 1,0 part, and this part will be a holomorphic connection. So you can think of this C-infinity flat connection by taking its 0,1 part and its 1,0 part as also defining a holomorphic connection on a holomorphic bundle, a different holomorphic bundle from the one you started with. Okay, so we get this identification, let's say, between the moduli space of Higgs bundles and the moduli space of flat holomorphic connections. Thinking of flat holomorphic connections, we then have you have a moduli space, so it's a complex algebraic variety or analytic variety. So you can see that we in this way, our space, if we just think of the space, we actually have two ways of thinking of a complex structure on it. One that comes because it's a moduli space of Higgs bundles, well, it's an algebraic moduli problem, but there's also the moduli problem of flat holomorphic connections, so also a complex structure. And when you look at this bijective correspondence, you realize that this is actually real analytic, but certainly doesn't respect the complex structures. So ultimately, the underlying, let's say, manifold or variety has two different complex structures. You can multiply them and get a third one, and that gives you exactly the whole two-sphere of complex structures, which is involved in a hyperkähler structure. Of course, you also need the actual hyperkähler metric, which you can write down using that harmonic metric that I talked about. Okay, so there's a so-called twistor space construction of this twistor space associated to this hyperkähler structure, and I want to just quickly explain that because it's necessary for, or at least enlightens what is the conformal limit construction. Okay, so what is the twistor space? So as a C-infinity manifold, basically you just take the product of a P1 together with just a copy of the moduli space. So let's say just the underlying real analytic variety. Okay, and then the idea is that you basically over each point of the projective line, you think of this as being parameterizing exactly the various complex structures in this hyperkähler S2 family of hyperkähler of complex structures that comes from the hyperkähler metric. And then this T has exactly that complex structure that at every point of here, your almost complex structure comes from exactly, well, you have it on P1, and here on M, you take the one corresponding to the point. Okay, so you put all the different complex structures together in a family. That's the idea. All right, so that's something general you can do for any hyperkähler manifold. You can write down this twistor space, and you can go to the paper and see how it's done. And then Deligne and Simpson gave a more algebraic interpretation of this twistor space construction through lambda connections. So what is a lambda connection? So it's a holomorphic connection again. Well, it's not quite a connection because it's a lambda connection, but it lives on a holomorphic vector bundle E. It is an operator that looks like a connection, so it takes the sheaf of holomorphic sections of E to holomorphic one forms, but you've deformed the Leibniz rule in this way that instead of having here just the usual Leibniz rule, you put a lambda out front on the pad that has to do with df. So you see that the concept of a lambda connection actually is very nice because it allows you to put into the same kind of object that of a Higgs bundle, which is what you get when lambda is equal to 0, right? Because here it simply says that your operator nabla is linear of a function, so it's like an endomorphism valued one form, which is just a Higgs field. And of course, for lambda equal to 1, this is just a definition of a holomorphic connection. So you can look at the so-called Hodge moduli space of all lambda connections. And this, you can actually, out of that, build the full twistor space. I'm not going to go into details with that. But what I want to just point out is that if you have the moduli space of lambda connections, then you can take your lambda connection here and simply you map it down to the corresponding lambda, and that gives you that almost that big open piece of the twistor space. Okay. And before I move on, I just want to say that also it's important to note that the usual C-star action on the moduli space of Higgs bundles, you can actually extend that to the moduli space of lambda connections. Okay, so when you have a C-star action, you can look at the corresponding Bialynicki-Birula stratification. Well, at least you need the existence of limits, but you have it. So let me try to explain the picture for the moduli space of Higgs bundle for the moduli space of lambda connections. So you have some fixed loci. I write them as F alpha, and so here you can see it's quite obvious that since you cover the usual multiplication by lambda action down here on the C, all fixed loci must lie over C. So these are the usual fixed loci in the Higgs moduli space. You get the corresponding stratification by these stable submanifolds of stuff that flows down to the F alpha fixed locus. And I'll just introduce this notation because I need it later, that W alpha 0 is then the stable manifold of this fixed locus in the Higgs moduli space. And this is the piece of the stable manifold, so the downward flow, the upward flow of this fixed point in the moduli space of lambda connection that actually lies here in the phi over 1, which is just the moduli space of flat connection, the Durand moduli space. Okay, so I've set up everything I need to explain to you what is the conformal limit. There's an important ingredient in this twistor space construction, which is something called the real twistor line. So this is something that exists in general and which is actually something that you have because, let me just show it to you here, because you have this product structure, then when you have these sections and you can show that they are actually they're real for some particular real structures on the base CP1 and on your twistor space. So Simpson, following Deligne, explains us what are these real twistor lines in the language of lambda connection, so in this specific case. And it's obtained like this. So you start with your Higgs bundle, and then what you do is you simply do more or less what we did when we wrote down the flat connection, except that you make some lambda modifications here when you multiply the adjoint of the Higgs field, and you also multiply here with lambda the 1,0 pad of the Chern connection associated to H. When you do this, you can check that actually this object here becomes a lambda connection. Okay, so we have here your twistor line, your real twistor line. And what is the idea of the conformal limit? Well, the idea is that for every positive R, you can move along your twistor line, and here you do something which looks a bit strange in the first place. But what you do is you start, well, at the first place you start with your Higgs bundle, then you multiply Higgs field by R. So see just the action by R over in the Higgs moduli space. Once you've done that, you move along the twistor line. So here, what are you doing? You're using the harmonic metric, which comes from R phi. Then you move out to the point lambda equal to R, which is here. So this is moving along the twistor line. And then you move yourself into the round moduli space just using the C star action, which since you need to go to 1, you have to multiply by R minus 1. Okay, so what does this give you? This gives you a holomorphic bundle, ER, which now depends, the metric depends on R, and you have this, this flat connection here. Okay, and now you try to make R go to 0, and if you can do that and you get a limiting flat connection over here in the round moduli space, this is what you call the conformal limit. Okay, so this is the construction. For later use, I've written down what is the flat connection. The existence of the conformal limit is known, as I said. It's proved, it was conjectured by Gaiotto, proved first by Dumitrescu, Fredrickson, Kidonakis, Mazzeo, Mulas, and Naitsky for what's called the Hitchin component, and then later by Collier and Wentworth, they proved it actually in more generality, which is the statement I'm going to give you. So what they say is that if you take a Higgs bundle whose C star limit at 0 is actually stable, so that's almost any Higgs bundle, in particular if you're in the co-prime case, it is any Higgs bundle, then you have a conformal limit. And you can say a lot more, because actually this, if you take here's your fixed point, right? It's the limit at 0 of your Higgs bundle. And here I take everything that flows to that under the C star action. Okay, and if I take some point here, I apply the conformal limit. Well, I know I have to go to the moduli space of flat connections. And what I go to is exactly the all the flat connections, which under the C star action on the Hodge moduli space flow down to the same fixed point. So here I have my W0. Over here, I have everything that flows over 1. So this is the lambda axis, right? And this is my W1. So this guy here and this guy here are identified by the conformal limit. Here, note that I have complex structure I, here complex structure J, and this map here is actually holomorphic. So it intertwines these two a priori completely different complex structures. Okay, so that's very beautiful. So to explain what we did, let me go to the rank 2 case. So I guess I don't have much time, but let me try to just quickly go over it. So let me maybe just move to the example which has the essence of what I want to say. So here's a very particular, important, famous fixed point of the C star action on the moduli space of rank 2 Higgs bundles. So what do? I take a square root of the canonical bundle of my Riemann surface, so holomorphic cotangent bundle, and I write down this rank 2 bundle, k to a half plus k to the minus a half, and I have a canonically defined Higgs field here of this shape, because basically this 1 is the canonical section that goes from k to the minus a half to the k to the half. Let's see, it goes the other way, it goes this way, right? So here, a map from here to here would be a section of k minus 1. Since phi is k valued, you have a tautological section there, a canonical section there. Okay, and this, let's look at what flows down to this. Well, what flows down to this are exactly all the Higgs bundles which have this shape. So you just modify this one by putting in this upper right-hand corner a quadratic differential. Okay, so that's the W0. Under the conformal limit, we know that it has to go to the corresponding W1. And what is the W1 there? Well, you also have an extension of k to the minus a half by something here went away. So you have an extension of k to the minus a half by k to a half like up here, but it's not a trivial extension, it's the unique non-trivial extension. And it turns out that there's a unique holomorphic connection whose second fundamental form, which is the operator you get by starting by the subbundle, using the connection, and then projecting to the quotient. With respect to this subbundle, there's this unique holomorphic connection which has this second fundamental form equal to 0. Hang on, this is wrong. This is not necessarily 0. It's only the top one. Okay, and then you can actually modify such holomorphic connections also by adding quadratic differentials in the place of this second fundamental form. So, what am I saying? I'm not totally sure this is right. I think this should be different than 0, and you add something in the other direction. I believe that is true. Yeah. Okay, so anyway, what's the point of this? So let's go to the relation to geometric structures. Hitchin very famously in his original paper on Higgs bundles, he showed that these W0, these Higgs bundles that flow to this particular fixed point, they actually have a geometric interpretation because they parameterizes all structures of a hyperbolic surface on X. Okay, so if you have Q equal to 0, in Hitchin's parameterization, you get exactly the uniformizing hyperbolic structure of the underlying Riemann surface, and then he shows how all the other quadratic differentials correspond to different hyperbolic metrics. So the Hitchin component here is really identified with the Teichmüller space of the Riemann surface. In a similar way, this other connection, this other component of all these holomorphic connections that can be built on this non-trivial extension and also parameterized by quadratic differentials, they actually parameterize the CP1 structures on X. So what's that? Those are geometric structures which can be given by Church, where the changes of coordinates are actually Möbius transformations, so natural transformations of CP1. So locally, X looks like an open set of the projective line. Okay, and how does that work? Well, in this case, this L is just our K2.5. Inside here, this is actually something that's transverse to our flat connection. What does that mean? That means that if I do take some flat trivialization on my bundle with respect to this flat connection, then this line is just a point in this corresponding projectivization. So I have actually a section, at least locally, which to each point in X gives me this line in the fiber, which is then a point in the projective space. So if I've trivialized, I get a map to CP1. Okay. The transversality condition exactly says that this is a local isomorphism. So I get my CP1 structure out of the flat connection and the transverse line bundle like that. Okay, and in fact, it was known that under the conformal limit actually makes this Q correspond to that Q. So the hyperbolic structure corresponding to this Q here gets mapped to the CP1 structure on X corresponding to this Q. But note that it's sort of very different in flavor because all these CP1 structures are compatible with the original Riemann surface structure. Okay, so they are all the CP1 structures that are compatible with the original CP1 structures. This is in particular, this is a holomorphic map, whereas these, of course, are different Riemann surface structures. Okay, so what we showed, so let me explain to you what we showed. So under some assumption, we write down actually something called a Beltrami differential. It's not so important exactly how you write it down. We use the harmonic metric, but the point is that the Beltrami differential defines a structure of Riemann surface. Okay, so this is exactly something that defines you a point in Teichmüller space. And there's a whole family indexed by these as. Okay, now we have for each R, we have our corresponding flat connection. Okay, we can take the 0, 1 part. Now, with respect to the Riemann surface structure mu, that gives us a d-bar operator, and it gives us a structure of holomorphic bundle over the new Riemann surface x mu that we've cooked up like this. Now, this C infinity, a priori C infinity subbundle, we can check that this actually defines a holomorphic subbundle, which is again transverse to this flat connection. So again, just as on the previous slide, I get actually a CP1 structure. And one for each R. So I have a family. I have a family of CP1 structures parameterized by R. So for R equal to 1, just to say what is the CP1 structure we have? Well, we actually recover Hitchin's parameterization of type Miller space. So this was known. If you notice here that for R equal to 0, this mu actually has an R here. So this becomes the 0 Beltrami differential. So the Beltrami differential measures the difference to your initial Riemann surface structure and the new one. So actually you get back to the original original Riemann surface structure on X. So you get back to the one in the OPA parameterization. So what we did basically is we exhibited the process of taking the conformal limit as passing through a family of Riemann surface structures that starts by the uniformizing Riemann surface structure coming from Hitchin's parameterization to the CP1 structure that you have coming from the OPA parameterization. So we gave this geometric interpretation of the process of doing the conformal limit. Okay, and I guess that's probably what I had time to say. So thank you for your attention.
Thank you, Peter. Are there questions or comments for Peter? There in the audience, maybe online. Well, I actually have a question for the rank 3 case. What about the rank 3 case? Have you explored the rank 3 case with Pedro?
Sorry, Ronald, I hear you not very. I think you're asking a question, but I couldn't quite hear you.
Have you explored the rank 3 case?
Good question. Yes. Well, certainly one would hope to be able to do something in higher rank. I mean, I didn't have time to go into it, so I just talked about also that very special uniformizing Higgs bundle, right? You can go to lower fixed points. You get some branched CP1 structures in that case. Another obvious question is higher rank, because the conformal limit certainly exists in higher rank, as I told you. So yeah, it's a very pertinent question. You probably have to limit the kind of Higgs bundles you look at to be able to make this construction. But yeah, something can probably be done. We're trying to think about how to do it. If you go to higher rank Hitchin components, certainly something should be doable. Whether you can do something for any kind of fixed point, I'm not sure, because you need somehow to be not too far removed from the canonical bundle to have something that in a natural way gives you this structure on the Riemann surface and gives you the Beltrami differential in particular. But yes, definitely there might be something to do in higher rank.
Thank you, Peter. So thank Peter again. And
well, thank you.
So there's a plenary talk right now here in the auditorium, and there's the coffee break after that, and we will resume with our session at 16:45 UTC -6 Costa Rica's time. Okay? Thank you very much.
Thank you. Bye-bye.
Bye, everyone. See you later.
See you later. Thank you.